Okay. Thank you. Can you hear me? Okay. 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 Well, thanks very much for coming, and also very thanks a lot to the organizers for this wonderful semester, where this work that just disappeared was done. Oh, yeah, here it is. So this work was done during the early part of the term, and so a little was done this morning. Mostly making the slides and doing one computation, which I'll show you at the end. So what I want to talk about is the Hasse principle for cubic forms. So the Hasse principle for quadratic forms states that if you have a quadratic form, f, it has a non-trivial rational zero if and only if it has a non-trivial zero over q nu for all places nu of q. Okay, so it tells you, so the Hasse principle for quadratic forms basically tells you that you have a non-trivial solution globally if and only if you do so locally. And so this principle is indeed what makes much of the theory of quadratic forms, the arithmetic theory of quadratic forms, so rich, is this local global principle that you can understand problems about representability of quadratic forms over the rationals by understanding the problem locally over the completions of the rationals. And you always have to keep in mind the completion at infinity, namely the real numbers, otherwise this is not true. Okay, so if f is a quadratic form, f equals 0 has a solution over the rationals if and only if it does over qp for every prime p and over the real numbers. Okay, so this is something that's very, very important in the arithmetic theory of quadratic forms. And so naturally, when people want to study higher degree forms, you want to know, well, how much of this rich arithmetic theory could be carried over to higher degree forms? And so the natural next question is, well, what about for cubic forms? So to what extent does the Hasse principle hold for cubic forms or higher degree forms? So, well, for binary cubic forms or even unary cubic forms, so in other words, cubic forms in two variables, the Hasse principle does hold. And this is not too difficult to see. So for binary cubic forms, the reason is essentially the same as for binary quadratic forms. So I'll do the contrapositive of the Hasse principle. So suppose f is a binary cubic form, if it has no rational root over the rational numbers, then that's the same thing as saying that it factors over a cubic field. And then if f factors over a cubic field but not over a subfield, then that means that there will be some p by the Chebyshev density theorem that makes f irreducible mod p. And if f is irreducible mod p, then f could have no root over qp. And so f has no rational root over q if and only if it doesn't have a root over qp for some p. And you'll notice that cubic was used in a very essential way in this argument. So try replacing cubic by quartic, the argument doesn't quite work. And in fact, well, okay, so what's really being used here is that f is irreducible is the same thing as having no rational root. And that's true only for quadratics and cubics, but it's not true beyond that. Okay, so the Hasse principle is true for cubic forms in one or two variables. And so there was a lot of work in understanding ternary cubic forms. In other words, cubic forms in three variables, homogeneous cubic forms in three variables. So to what extent does the Hasse principle hold there? Well, it doesn't always hold. So the local global principle is not true anymore if you have cubic forms in three variables. And in 1957, Selmer gave the famous counterexample to the Hasse principle, namely 3x cubed plus 4y cubed plus 5z cubed. So this special cubic polynomial, it has non-trivial zeros over q nu for all nu. In fact, it has a solution mod p for every p that lifts to zp. But it has no rational zero. So in other words, the plane cubic curve cut out by 3x cubed plus 4y cubed plus 5z cubed, it has a local point at all places, but no global rational point. Okay, so this is a counterexample to the Hasse principle. And so a natural question that arises is, well, how frequent are such counterexamples to the Hasse principle among all plane cubic curves? Is Selmer's example rare, or is it very frequent? What is the expectation if you choose a random plane cubic? Do you expect to get a counterexample to the Hasse principle, or did Selmer have something that occurs very rarely? So more precisely, suppose if we take all ternary cubic forms and we order them by their coefficient height. Okay, so the sizes of their coefficients, that's the natural way that one would pick random ternary cubic forms. So if we order all ternary cubic forms by their standard coefficient height, in other words, the maximum of the absolute values of the coefficients, then we can ask, if you order all forms by that height of the coefficients, what proportion of the resulting plane cubic curves will fail the Hasse principle? Okay. In other words, what proportion of those plane cubic curves will have a local point at all places, but no global rational point? So some of these plane cubic curves will be degenerate and won't really give a plane cubic curve. For example, the 0 ternary cubic won't really give a curve, but those things are rare. So we throw out all those things. They have 0 density anyway. So you can order all ternary cubic forms by coefficient height, throw out the ones that are degenerate because they have density 0 anyway. And then the resulting plane cubic curves, you want to ask, how often do they fail the Hasse principle? Okay. They have a point locally, but not globally. So more formally, if we let n fail of x, denote the number of ternary cubic forms having coefficient height less than x that fail the Hasse principle. Okay, so that's all the things that fail and have coefficient height less than x. That's counted by n fail of x. And if you let n tot of x denote the total number of ternary cubic forms having coefficient height less than x. So in other words, n tot of x is about 2x plus 1 to the 10th, because there are 10 coefficients of a ternary cubic form. And they can basically go between minus x and x. So you have about 2x to the 10th such forms having coefficient height less than x. Then the question we're asking is, does the limit of n fail of x over n tot of x as x goes to infinity, does that limit, first of all, does it have a value? Does it exist at all? And if so, what is its value? What value do we expect? Integers, yeah, integral ternary cubic forms. Yeah. So I first heard this question from Bjorn Punin in his Ober-Wolfach lecture in 2007 at Explicit Methods in Number Theory, organized by Cohen, Leinster, and Zagier. I mentioned that because 2 of the 3 organizers are here. And so Punin asked this question, which apparently goes back before him, but he had a very nice perspective on it, and Punin and Volek have a wonderful paper on this topic in which they discuss what the possible answers could be, although they declined to make any conjecture on the value of this limit in their paper. But on math overflow, this is where you really find out what people are thinking. So and on math overflow, Bjorn did make this informal conjecture, which he attributes to Swinnerton Dyer, but he gives some heuristics for why he would also guess this to be true. He guessed that the limit 1 should be 0. So in other words, if you, the proportion of all ternary cubics, integral ternary cubics, if you order them by coefficient height, the proportion that have the property that they fail the Hasse principle should become negligible as x goes to infinity, should be 0. So in other words, Selmer's example is very special in their view. Okay, so I think that's the only conjecture on this issue that I could find, although Bjorn mentions on Math Overflow that people have guessed everything between 0 and 1. Lots of numbers between, including 0 and 1. Okay, so what I want to show in this lecture is that, in fact, a positive proportion of plane cubics fail the Hasse principle. That is, so the theorem is that if you take the lim inf of n fail of x over n tot of x, that is actually positive. Okay, so the proportion is bounded below by something that's positive.
What is Bjorn or Swinnerton Dyer's conjecture based on?
I didn't really understand. What was their conjecture based on? I didn't really understand the heuristics, I guess. But you can see it on Math Overflow. I didn't really. Well, I guess given this theorem, I guess it's a good reason not to understand it. But but I don't know. No, there may be. Yeah. No, I don't really. I'm not really sure.
Does this actually oscillate, or?
No. So at the end, I'll actually I'll conjecture a precise value for this. In fact, and I think that it doesn't oscillate, and I think it has a precise value, which I'll tell you at the end. But first, I want to show that it's positive.
So the limit does not exist in the end?
Oh, I think it probably does. All I show that is that the lim inf is positive. But I conjecture that it does exist, and I'll give you the precise value. Yeah. So in this theorem, the constant could be made effective, although I won't do that here. But I think I can get it up to about 30%, provably. But I won't get into that here. I just want to show that it's positive. So how does one prove this? So the main ingredients in proving this theorem are the recent results with Arel Schenker that I talked about in the introductory workshop. And so I just want to review that here. So it's on the work on the average size of the P-Selmer group of elliptic curves. And the results that we'll need here are for p equals 3 and p equals 5. So we need the average size of the P-Selmer group for p equals 3 and p equals 5, together with the fundamental domain covering method that I've been talking a little bit about this term at MSRI. So to state the results that we need, recall that any elliptic curve over Q can be expressed as EAB, y squared equals x cubed plus ax plus b, with the property that a and b can be chosen to be integers, with the property that if p to the 4 divides divides a, then p to the 6 divides b. So every elliptic curve E over Q can be expressed in this form. There's an isomorphism. Sorry? Oh, p to the 6 does not divide b. Yeah, absolutely. P to the 4 divides a implies p to the 6 does not divide b. Sorry, I'm not quick enough to change this in real time. Yeah, right. Yeah, well, please change that if you're taking notes. P to the 6 does not divide b. So in other words, if p to the 4 divided a and p to the 6 divided b, then you could reduce a by a factor of p to the 4 and b by a factor of p to the 6, so that this didn't happen. Okay, and we define the naive height of a rational elliptic curve. You take its canonical form EAB, and you take the maximum of the absolute values of a cubed and b squared, because those are the things that are comparable. Okay, so that's the naive height of an elliptic curve EAB. Okay, it's just the sort of the maximum of the sizes of its defining equation coefficients. Okay. Okay. So then the result with Arel Schenker is as follows: that when you take all elliptic curves and you order them by their naive height, then the average size of the 2-Selmer group is exactly 3. Okay. And the average size of the 3-Selmer group is 4, and the average size of the 4-Selmer group is 7. And the average size of the 5-Selmer group is 6. So the way to think of these all at once is that the average size of the n-Selmer group is the sum of the divisors of n, for n less than or equal to 5. Luckily, we don't need more than 5 for this particular application. Okay, so the proof is, so I've been talking about it this term, but it's a geometry of numbers method applied to certain spaces, namely the spaces of binary quartic forms, ternary cubic forms, pairs of quaternary quadratic forms, and quintuples of 5 by 5 skew-symmetric matrices. So one takes the integral elements of each of these spaces, and one counts equivalence classes of points in these spaces having bounded height. Height is defined in terms of the maximum of the size of the invariance of the natural group that is acting on these spaces. We get a count of that, and then we sieve to get Selmer elements. So there's that's where the majority of the work is in this sieve. Okay, but what I want you to take from this is that we expect the average size of the n-Selmer group to be the sum of the divisors of n. Okay, and that's a theorem for n less than or equal to 5. Even n equals 1. Okay. So how is this used? So the point is, just knowing the 3-Selmer group average wouldn't have been enough, and you'll see this in a second. So these results, first of all, I want to point out that these results give bounds on the average rank of elliptic curves. So if you know that the average size of the 2-Selmer group is 3, then that tells you, if you work it out, that you can't have an average rank of elliptic curves more than 1.5. So the result on 2-Selmer tells you that the average rank of elliptic curves is at most 1.5. If you work out what the 3-Selmer result tells you, it tells you that the average rank of elliptic curves is at most 1 1/6. And the 5-Selmer result tells you that the average rank of elliptic curves is at most 1 1/20. Okay, so each P-Selmer, as P gets larger, the average size of P-Selmer seems to give a better bound on the rank, a better upper bound on the rank. And that's sort of what's behind the main theorem about the Hasse principle, is that morally this implies that lots of 3-Selmer elements, right, because the 3-Selmer result only gives you a bound on the rank of 1.17, whereas we know from the 5-Selmer result that the average rank isn't actually that high. And So what that tells you is that lots of 3-Selmer elements must be coming from non-trivial elements of SHA. Okay, so that's what sort of morally this is telling you, but how do you, I want to make that precise. But this was where the idea came from, is that, well, if one Selmer average is giving you better results on another than another Selmer average, then that means you're learning something about the distribution of the Selmer elements and whether they can all really be coming from rank. Okay, so that's sort of morally what's behind the story. So first what I want to do is I want to just look at 3 Selmer elements, not ternary cubic forms, but let's look at 3 Selmer elements of elliptic curves. Let's order all elliptic curves by height and look at 3 Selmer elements of those elliptic curves up to height x, where x is large. And I want to show that a positive proportion of all 3 Selmer elements of elliptic curves up to a given height don't have a rational point. Okay? In other words, they fail the Hasse principle. Okay, so that's the theorem, is that a positive proportion of 3 Selmer elements of elliptic curves, okay, when those Selmer elements are ordered by the height of their Jacobians, the naive height of their Jacobians, then a positive proportion of 3 Selmer elements don't possess a rational point, and thus they fail the Hasse principle. Okay, so how does one prove this? Using those Selmer averages? Well, let's suppose not. Okay, so suppose that 100% of elliptic curves have the property that the size of the 3 Selmer group is just 3 to the rank. Okay? In other words, the Selmer group is coming entirely from rank, not from SHA. Right? So if we assume that all 3 Selmer elements have a rational point, then that implies that the 3 Selmer group has size 3 to the rank for 100% of elliptic curves. The reason being that 0% of elliptic curves will have rational 3 torsions, so they won't contribute anything to the 3 Selmer group. So if 100% of 3 Selmer elements have a rational point, then for 100% of elliptic curves, the 3 Selmer size is 3 to the rank. And so what that means is that if you take 2 times 3, 2 times 3, well, 3 is the average size of the 3 Selmer group minus 1, right? Right, okay, so 3 we're rewriting as the average of 3 to the rank minus 1, because 3 to the rank minus 1 is the size of 3 Selmer, and the average size of 3 Selmer was 4. Right? So if you subtract 1 from 4, you get 3. So that's another way of writing 3. Okay, everyone good here? Okay, now we use the fact that 3 to the n minus 1 is less than, 2 times 3 to the n minus 1 is always less than or equal to 5 to the n minus 1. Okay, so if you think about it, 3 to the integer minus 1 is always going to be 2 times 3 to the integer minus 1 is always going to be less than or equal to 5 to the integer minus 1, with equality when the integer is 1. Okay? And now average of 5 to the rank, so we only need to know that on integers, and luckily that's true on integers. And 5 to the rank minus 1 is bounded above by the size of the 5 Selmer group. And we know that the average size of the 5 Selmer group is at most 6. So the average size of the 5 Selmer group minus 1 is at most 5. Okay, so we get that 2 times 3 is less than 5, and that's a contradiction. So what that means is that some positive proportion of the 3 Selmer elements, when you're counting all 3 Selmer elements up to height x, as x goes to infinity, will not possess a rational point. A positive proportion won't possess a rational point. And of course, you can make this effective and get bounds on how many would have to fail the Hasse principle. But this is saying that a positive proportion of 3 Selmer elements do not possess a rational point. Okay, so this is kind of close to the result we were looking for, namely that a positive proportion of ternary cubics fail the Hasse principle. So we have to understand what is the connection between 3 Selmer elements and ternary cubics. That's one thing we have to understand. The other thing is we're counting in a totally different way. Here we're counting by the height of the Jacobian, the naive height of the Jacobian. And the result we're looking for is counting in a box by coefficient height on the ternary cubic form. So those are two things that separate this theorem from the theorem that we're actually looking for, and that's actually a major issue. Okay, but this is part of the way it's saying that a positive proportion of 3 Selmer elements, when you order them by the heights of their Jacobians, do not possess a rational point. Okay, so they fail the Hasse principle. Okay, so this produced a lot of 3 Selmer elements that fail the Hasse principle. So how do we deduce theorem 1 from this? So to do this, we have to understand some of the invariant theory of ternary cubic forms. So GL3Z acts naturally on integral ternary cubic forms by change of variable. And that action has 2 polynomial invariants, which are traditionally called S and T. And they have degrees 4 and 6, respectively. And the theorem that relates 3 Selmer elements to ternary cubic forms is the following, which is due to Castles and made very precise over the integers by Cremona, Fisher, and Still, which says that there exists a map from the 3 Selmer elements of the elliptic curve EAB, where A and B have that minimal property, right? That p to the 4 divides A implies that p to the 6 doesn't divide B. So if you have such a minimal representative of the isomorphism class EAB, then the 3 Selmer elements of EAB injectively map into the GL3Z orbits on integral ternary cubic forms whose invariants are A and B. So the invariance of the elliptic curve can be made to be identified with the invariance of the ternary cubic form. So that's a remarkable thing. It says that if you take the elliptic curve with invariance A and B, then you can take its 3 Selmer elements and identify them with certain orbits of ternary cubic forms having exactly those invariants, A and B. So you can view the 3 Selmer elements as a subset of ternary cubic forms where the invariants match up. And furthermore, the reducible ternary cubic forms, I'll explain what that means in a sec. Reducible consists of, so reducible just means that it has a rational flex. So the inverse image of the ternary cubic forms that have a rational flex correspond to the identity element of the Selmer group. Okay, but the point here is that the 3 Selmer group elements have been identified with ternary cubic forms, integral ternary cubic forms. And since a positive proportion of the Selmer elements fail the Hasse principle, as we just saw, it seems to mean that it produces lots of ternary cubic forms that fail the Hasse principle. So it seems that theorem 1 is almost proved. Okay, but of course, it's a different way of counting. Right? We haven't taken ternary cubic forms in a big box. We're sort of identifying some of them with Selmer elements of EAB and then ordering them by the size of A and B. And that's a little different. Okay, so how do we get theorem 1 from this? At least we now have lots of ternary cubic forms that fail the Hasse principle. So the way we do it is we first, instead of proving that a positive portion of ternary cubics fail the Hasse principle in a big box, we first prove it for a fundamental domain for the action of GL3Z on the real vector space of real ternary cubic forms. Okay. So let F be such a fundamental domain for the action of GL3Z on the space of real ternary cubic forms. Okay. And we'll say that a ternary cubic form is irreducible if the common 0 set of F and its Hessian has no rational points. So it's reducible if it has a rational flex. It's irreducible if it doesn't have a rational flex. Then one of the ingredients that went into to proving this result about 3 Selmer with Shankar is the following, is that there exists a constant C, which is basically the volume of F of all elements that have height less than x. So there exists a constant C bigger than 0 such that the number of irreducible ternary cubic forms in F satisfying S cubed less than x to the 12th and t squared less than x to the 12th is that constant times x to the 10th asymptotically. Okay. So this is telling you the number of irreducible. Okay, irreducible, remember, means that it doesn't have a rational flex. So the number of irreducible ternary cubic forms that are in the fundamental domain with this property that the invariants are bounded is asymptotically this constant times x to the 10. Okay. And so how can one understand what that means? So one way to see it is that if you take the volume of fx, which is the fundamental domain intersected with the condition that s is less than x to the 12th and t is less than x to the 12th, right? Theorem 5 is counting the number of irreducible elements in this region. Right? And the volume of that region is actually cx to the 10th. So what theorem 5 is saying is that the number of irreducible ternary cubic forms in this region F, cut off by the invariance being less than x to the 12th in that way, is just the volume of that region. Okay? So the number of irreducible elements, integral points in that region, is the volume of that region. So theorem 5 is very natural in that sense. It's just saying that the number of integer points in a certain region is the volume of that region. But there is a subtlety in this, which is that this fundamental domain for the action of GL3 is not compact. And that's where all the subtlety is, actually. So fx is not compact And the theorem would actually be false if you dropped the word irreducible. That's why I'm putting a lot of emphasis on this irreducible. If you're counting the irreducible points, do you get this asymptotic that way? And it's actually false if you remove the word irreducible. And what's behind that is that fx, this region fx, is not compact. It has a cusp going off to infinity. And there are lots of points in the cusp, but you can prove that 100% of those points in the cusp are reducible. And the main body consists of mostly things that are irreducible. And so then if you just count the number of irreducible points, that turns out to be about the volume. But if you included the reducible ones, the count would blow up. So the cuspidal part, the tentacle part, it has a tentacle going off to infinity, that contains basically the reducible forms. The main body contains the irreducible forms, and that's what's behind this theorem. So that even though we have a non-compact region, we can say that the set of irreducible points, that its count is about the volume, even though that wouldn't be true if you included all points. Okay, so we have a count of irreducible points inside the fundamental domain. Okay, so this is an important point. So how do we use this fundamental domain to obtain theorem 1? Well, let d x to the 10th denote the asymptotic number of elliptic curves having height at most x to the 12th. Okay. So that's an easy count to do because you're just counting the number of a and b such that a cubed is less than x to the 12th and b squared is less than x to the 12th. So that's a constant times x to the 10th. Then the fact that the average size of the 3-Selmer group is 4 means that, well, you have 4 times d x to the 10th asymptotically number of 3-Selmer elements of those elliptic curves. And the number of non-identity elements, in other words, the irreducible ones, will be one less, will be dx to the 10th less, namely 3dx to the 10th. Okay, so 3 is 4 minus 1. Okay? The 1 corresponds to the reducible ternary cubic forms, which correspond to the identity element of the Selmer group. So the fact that the average size of the 3-Selmer group is 4 means that there are 3dx to the 10th locally soluble irreducible ternary cubic forms in fx. And what we showed already is that when we ordered these by the height of the Jacobian, the positive proportion of them failed the Hasse principle. So if these strictly less than 100% have a global point, okay, they fail the Hasse principle. And so there exists some e bigger than 0 such that at least e x to the 10th of the irreducible ternary cubic forms in this fundamental domain fail the Hasse principle. Okay? So at least in a fundamental domain now, we see that a positive proportion of the ternary cubic forms fail the Hasse principle. And so we have the result in a fundamental domain now, and now we want to translate that into counting ternary cubic forms in a box and showing that a positive proportion of those fail the Hasse principle. And so the way to do that is you take this fundamental domain, which is a non-compact thing, and because it has finite volume, if you take a very, very large box, you can cover an arbitrarily large proportion of that fundamental domain, volume-wise. So for r bigger than 0, if you consider the box B of Rx, where R is a parameter, okay, which consists of all ternary cubic forms having height less than Rx, then if you choose R large enough, you can make the volume of the fundamental domain intersected with that large box an arbitrarily large proportion of the volume of the fundamental domain. Even though the fundamental domain is non-compact, it has finite volume, so you can cover it with a large enough compact thing to get an arbitrarily large proportion of the volume. So we're going to choose R large enough so that the volume of the intersection of the box with the fundamental domain is a large proportion of the total volume. And we'll make that proportion 1 minus e minus epsilon over c. So remember, e was the asymptotic for how many failed the Hasse principle. C was the total asymptotic. Okay, so we just want to make it a little bit bigger than 1 minus e over c. Okay. So we'll choose some epsilon bigger than 0, tiny, so that this covering by the box intersects the fundamental domain in a proportion that's bigger than 1 minus e over c. So now this intersection is compact because we intersected it with the box. And so since you've intersected with something compact, and that as that compact thing homogeneously expands, the proportion of reducible elements, in other words, those that have a rational flex, that proportion will go to 0. And so one can prove that formally, but one way to see that is that it becomes negligible because all the reducible stuff is in the cusp. And if you're intersecting with something compact, then sort of 0% of the things in there will be reducible. Or another way to think about it is that if you sort of take a random ternary cubic ordered by coefficient size, the chance that it has a rational flex will be 0. Okay, that seems believable, and it's actually provable. And so we see that the number of irreducible ternary cubic forms in the intersection of the fundamental domain with this large box is asymptotically this proportion of the volume times the total volume. So it's c minus e plus epsilon times x to the 10th. So this volume is in a compact region. It's contained in a box. And this gives the estimate of the number of irreducible points in that volume. But we know that at least this many fail the Hasse principle. At least e x to the 10th fail the Hasse principle. And since we have more than c minus e plus epsilon points, that means at least epsilon x to the 10th of these must have failed the Hasse principle. So what we did is we produced some things that failed the Hasse principle, a positive proportion of things, irreducible things that failed the Hasse principle in this fundamental domain. And then we just chose a big enough box so that we're sure that we will hit some of them. And so we've made a big enough box so by choosing R large enough so that some power of some constant times x to the 10 actually fail the Hasse principle for some positive constant. And since the box has volume on the order of x to the 10th, that's giving us a positive proportion of things in the box that are failing the Hasse principle. Okay, so we've produced epsilon x to the 10th irreducible ternary cubic forms that fail the Hasse principle. But B of Rx also has volume on the order of x to the 10th. And so what that means is that so epsilon times x to the 10th, things fail the Hasse principle in this box, and the number of elements in the box is also on the order of x to the 10th. So a positive proportion of things in the box also will fail the Hasse principle. Okay, and so that proves theorem 1. So the idea was that we first used the Selmer elements, comparing 3 and 5 to show that lots of 3 Selmer elements have to fail the Hasse principle. And then we compare the 3 Selmer elements to ternary cubic forms in a fundamental domain. So inside a fundamental domain, you see that a positive proportion of ternary cubic forms fail the Hasse principle. And then you intersect the fundamental domain with a large enough box so that you get that positive proportion of things that are failing the Hasse principle inside the box. And the reason you don't miss all the things that fail the Hasse principle is because the cusp contains all the points that automatically have a global point because they're the identity element of the Selmer group. So this cusp issue is very, very important. It says that all the things, if you go far in the cusp, they're all going to be reducible. They'll all have a global irrational point, namely a rational flex. And if you stay away from that, then that's the only place where you can hit things that fail the Hasse principle. And since a positive portion of things were failing the Hasse principle in the fundamental domain, they will fail it in a large enough box covering the fundamental domain. Okay, so there's some subtle counting issues going on with the geometry of the fundamental domain, which, if they weren't true, then one couldn't have proven this result. Okay, so I know it's a little bit of a complicated argument. Are there any questions about?
How do you get this up to 30%?
You have to sort of make effective how big you can take the epsilon against how much volume. Well, so when you take a bigger box, you can get more of that epsilon. First, you try to make epsilon as big as you can, and that you have to use the best rank bounds that we have in order to do that. And then you adjust R so that you get as much of that epsilon that you can. But then, of course, the volume of the box is getting bigger, and so you lose that way. So you have to do a balancing act there. Yeah. Someone else had a question? Oh, no. Okay. Okay. Okay, so that proves that even when you're counting by coefficient height, a positive proportion of ternary cubics fail the Hasse principle. Okay, so what do we expect the true density to be? A failure of Hasse principle. So the one ingredient that you need in order to make a conjecture now is the rank distribution conjecture. It says that 50% of elliptic curves have rank 0 and 50% have rank 1 if you order them by their naive height. And that allows, if you assume that distribution conjecture, together with the techniques that I just talked about, it allows us to make a very precise conjecture regarding the exact density of the failure of the Hasse principle. And so the way that goes, you proceed in the same way that we did, but now we can make precise what proportion of 3-Selmer elements will be failing the Hasse principle when you order those 3-Selmer elements by the naive heights of their Jacobians. So the theorem is, assume the rank distribution conjecture. Okay. Then what proportion of 3-Selmer elements, when you order them by the heights of their Jacobians, will fail the Hasse principle? Well, so I claim the answer is 1/2. So 1/2 of all 3-Selmer elements will fail the Hasse principle. And, well, the reason is that for an elliptic curve, the elements of the 3-Selmer group that have a rational point correspond to the elements of E mod 3E. Right? The ones that don't have a rational point will come from the non-trivial elements of SHA. They'll be cosets of E mod 3E. Okay, so the ones that have a rational point correspond to the elements of E mod 3E. So we basically need to know what is the average size of E mod 3E. Well, if we assume the rank distribution conjecture, half the time E mod 3E will have size 1, and half the time it'll have size 3, 3 to the 1. So I'm assuming slightly more than the rank distribution conjecture, namely that ranks don't blow up like crazy on the 0% of places where they don't have rank 0 or 1. So the average size of E mod 3, assuming the rank distribution conjecture, is just the average of 3 to the rank. So 3 to the 0 will happen half the time, and 3 to the 1 will happen half the time. So if you divide that by 2, you get 2. Okay. So the average size of E mod 3E we expect to be 2. On the other hand, we know that the average size of the 3-Selmer group is 4. Okay. And 2 divided by 4 is 1/2. Okay, so what that means is that 1/2 of all 3-Selmer elements fail the Hasse principle. That's what this is saying. So it's 50-50 chance. If you pick a random 3-Selmer element of elliptic curves at bounded height, exactly half will fail the Hasse principle, half will have a rational point. And if you do the same computation for p-Selmer, for p any prime, well, if you want it to be a theorem, you have to choose p less than or equal to 5. The answer half, that's what comes out. If you take p, so that's what I expect in general, is that if you take a random p-Selmer element, the chance that it has a rational point is a half, okay, by the same computation. Okay, so that's a theorem, assuming the rank distribution conjecture. So let n locally soluble of x, denote the number of integral ternary cubic forms of coefficient height less than x that have a local point at all places. Okay. Then Poonen and Volek proved in that paper that I mentioned is that if you take the asymptotic proportion of the locally soluble things over all things, that approaches a definite limit, C, which is the product of the local densities of locally soluble ternary cubic forms. Okay. And in fact, so that's a theorem, and in fact they prove that C is strictly between 0 and 1. So the proportion of locally soluble ternary cubic forms among all ternary cubic forms has a definite proportion, C, and that number C is between 0 and 1. And in fact, we think that CP is explicitly computable. This is joint work with John Cremona, which we're just finishing. But numerically, you can work out what C is. And it turns out to be very large. So if you take a random ternary cubic, the chance that it has a local point everywhere is very high, 0.96. Okay, and that's actually a theorem. So most ternary cubic forms locally have a point everywhere. And since 1/2 of all Selmer elements fail the Hasse principle, we might also expect that, well, the proportion of soluble things among all locally soluble things is a half, right? Because the locally soluble things are kind of 3-Selmer elements, and the soluble things we saw among 3-Selmer elements are 1/2 of them. And this is true if you're counting 3-Selmer elements by the heights of their Jacobians. But suppose we're counting in a box. This is what we're doing, right? Then do we still expect it to be a half? Right? Do we expect 1/2 of locally soluble things to actually be soluble, even if we're ordering by coefficient height? And, well, the answer is no. And the reason is that in a homogeneously expanding box, as I explained earlier, if you take a homogeneously expanding box, the number of ternary cubic forms having a rational flex has density 0. Okay? Because if you're in a homogeneously expanding box, you're avoiding the cusp of the fundamental domain. So you're not hitting any of the identity elements of the Selmer group. Right? You're the identity element in the 3-Selmer group exactly if you have a rational flex. But the chance that a random ternary cubic form, when ordered by coefficient height, has a flex is 0. So basically, you're not going to hit the identity elements of the 3-Selmer group in this way of counting. Okay. So one way of thinking about this is identity elements lie in the cusp of fundamental domains. You won't pick them up in compact expanding regions. And this is something that one can prove, is that you really have, if you order all ternary cubic forms by coefficient height and get bigger and bigger, take bigger and bigger coefficients, the proportion that have a rational flex will be 0. So in other words, you will never be seeing the identity elements of the 3-Selmer groups. So what that means is that the limit of n sol over n log sol will be the average of E mod 3E minus the identity element divided by the average of the 3-Selmer group minus the identity element, which is not a half, but actually 1/3. Okay, so if you look at among all 3-Selmer elements, you have 1/2 probability of having a rational point. But if you, among ternary cubic forms in a homogeneously expanding box, the chance that you have a point if you're locally soluble is only 1/3. Which means that we expect that n fail over n locally soluble to be 2/3. And that is, the chance that you fail the Hasse principle is actually higher when you're counting ternary cubic forms in a box. So the chance of failing the Hasse principle is very high. It's 2/3. If you're locally, so if you pick a random locally soluble ternary cubic, the expectation is that you're going to fail the Hasse principle with probability 2/3. And so what that means is that Selmer's example is not so rare. At least 2/3 of all locally soluble plane cubics, assuming this rank distribution conjecture, will fail the Hasse principle. And again, most curves are locally soluble, 0.96 of them. So if you pick a plane cubic curve at random, then you can expect that 0.96 times 2/3, that is 64% probability that it will fail the Hasse principle. So if random ternary cubic in the plane has a 64% probability. That's what I feel is the probability that it will fail the Hasse principle. So in other words, Selmer's example gives more of the typical behavior rather than being rare. Or inspired by Henrik's talk this morning, I could say, plane cubic curve is more likely to fail the Hasse principle than not. Yeah, a 64% chance. Okay. Right. Okay, so that's what I feel is it. So I feel that it's about 64% chance if you pick a random plane cubic that it will fail the Hasse principle. And okay, so there are various variants that one can ask. For example, if you take equations of the form y squared equals a binary quartic, you can ask, well, what proportion of those fail the Hasse principle? So if you look among all binary quartic forms, and you ask, I want it to represent a square, okay, how often will it locally have a solution everywhere but no global solution? So this was actually the first studied case. This is pre-Selmer. So in 1940, Lind and Reichert showed that the equation y squared equals 2x to the fourth minus 34z to the fourth has a local solution at all places, but no global rational solution. So this was sort of the first really discussed example of the failure of the Hasse principle in a small degree case. But it was for a quartic. Y squared equals a binary quartic. And this was 17 years before Selmer. And so we can ask, how rare are such counterexamples among all binary quartic forms? If we order all binary quartic forms by coefficient height, what is the probability that y squared equals f fails the Hasse principle? That is, has a local point everywhere but no global point. So using 2 Selmer arguments instead of 3 Selmer arguments, but still using 5 Selmer, one can prove the same kind of theorem, that a positive proportion of integral binary quartic forms, when ordered by coefficient height, fail the Hasse principle. The proportion changes a little bit. So maybe I'll just say that quickly since I have. The proportion changes a little bit. So it's still true that if you assume the rank distribution conjecture, then, okay, so that was a theorem, and now I'll go conditional just to say what we expect. So if you assume the rank distribution conjecture, then when 2 Selmer elements of elliptic curves are ordered by the naive heights of these elliptic curves, then exactly half of them fail the Hasse principle. Okay, it's the same as for 3 Selmer. So that number half doesn't change, but But the number 2/3 changes. When locally soluble integral binary quartic forms are ordered by coefficient height, it's not 2/3, but a proportion of 3/4 of them have the property that y squared equals f, fails the Hasse principle. So I think that for binary quartic forms, the y squared equals f problem, even more of those things fail the Hasse principle, y squared equals f. And the way we get the 3/4 is exactly the same argument as we used to get 2/3. Okay? But because the average size of 2 Selmer is only 3 instead of 4, that changes the constant a little bit. So the probability actually goes up a little bit for the failure of the Hasse principle for binary quartic forms as opposed to ternary cubic forms. Okay, I'll stop there. Thanks.